Okay, let's just jump right in. Picture this. You're 30,000 feet up in the air, flying through a pitch-black sky. Outside your window, the clouds are churning. The storm is literally screaming, and heavy rain is just pelting the wings. Then, suddenly, bam, a massive, blinding bolt of lightning. We're talking a current hotter than the surface of the sun, strikes the very nose of your airplane. There's this deafening crack. But inside the cabin, you don't even spill a drop of your coffee. The lights overhead don't even flicker. You are perfectly, completely safe.
Why doesn't that electricity just rip through the cabin and fry everything inside? I mean, is it just incredible luck, or is there some kind of invisible mathematical shield protecting you? Well, in this explainer, we're going to build up this concept step by step. We're going to connect the dots like a movie mystery, uncovering the universe's invisible forces to solve exactly how you survive.
To solve this modern aviation mystery, we actually need to gather a few fundamental clues. And to find our very first one, we have to travel all the way back to the shores of ancient Greece, roughly 2,600 years ago.
There was this philosopher, Thales of Miletus, and he noticed something kind of weird. He saw that when he rubbed a piece of amber, it suddenly got this strange new power. It could pull in tiny little bits of dust and fluff. Now, it might sound like a simple party trick, right? But that little observation, that was the very first thread pulled in a mystery that would take millennia to solve. For centuries, that's all it was, a curious little fact. The mystery just lay dormant. But then you fast forward to the 1600s, and an English scientist named William Gilbert, he picks up the trail. He started experimenting and discovered, wait a minute, it's not just amber. A whole bunch of different materials. When you rub them, they get this same strange, attractive power. Suddenly, the case was way bigger. So Gilbert figured, hey, this thing needs a name. You can't investigate something without a name. And he looked all the way back to that very first clue, the amber. Well, the Greek word for amber is electron. And so he called this unseen force electricity. And just like that, for the first time, the ghost had a name. Okay, so the force has a name, the investigation can really start. And the next generation of scientists, they weren't just happy to watch it happen. They wanted to get in there and decode its very nature. And what they found? Oh yeah, the plot was about to get a whole lot thicker. So this French scientist, Charles Dufay, he finds this massive clue. This force isn't just one thing. It seems to have two distinct flavors. One he called vitreous, which he got from glass, and the other resinous from our old friend amber. But leave it to good old Benjamin Franklin to just simplify the whole thing with a stroke of genius. He gave them the simple, powerful names we still use to this day, positive and negative.
It's a really simple way to think about it. If you're positive, you have a deficit of electrons. If you're negative, you've got a surplus. That's it.
And these charges, they live by one simple, unbreakable rule. Opposites attract and likes repel. So two positive charges, they're going to push each other away. Two negative charges, same deal. But bring a positive and a negative charge near each other, and they'll pull together. This single idea is the foundation for everything we're talking about today.
All right, so now we know there are positive and negative charges. We know they attract and they repel. But you know, for any investigator, the next big question is always about scale. It's great that it exists, but just how strong is this invisible pull? The man who would finally answer that question was Charles Augustin de Coulomb. He used this incredibly sensitive device, something called a torsion valence, and he set out to actually measure this force with real precision. And what he found? Wow, it was the breakthrough. We call it Coulomb's law. It gave us the actual math to predict the force. Basically, the more charge you have, the stronger the force. But here's the kicker. As you double the distance between the charges, the force doesn't get cut in half. It drops by a factor of 4. For the very first time, this unseen force was predictable. You know how it is in these stories, right? You solve one mystery, and it just opens up an even bigger, deeper one. Coulomb's law worked perfectly, but it implied something that really bothered physicists. It described a force that could act across totally empty space, instantly. I mean, think about it. This was the central paradox. How can one charge over here know that another charge is way over there, with nothing but vacuum in between them? How can any force act without touching? It felt like magic, not science. And the answer, funny enough, it didn't come from some high-level mathematician. It came from a brilliant experimentalist with an incredible imagination, Michael Faraday. He put forward this radical idea that would change physics forever. He basically said, what if the charges aren't talking to each other directly? What if there's a middleman? So Faraday had this incredible idea. He imagined that every single charge creates this field in the space all around it. It's like an invisible alteration of the very fabric of the universe. It's the field that the other charge actually feels. So there's no spooky action at a distance. A charge feels a force from the field that's right there at its own location. This was a total game changer.
Okay, so we know lightning is basically just a massive transfer of electrons onto the metal skin of our airplane. But to actually prove why the passengers are safe, we have to look at the forces at play. A lightning strike doesn't just involve a couple of electrons, right? We're talking about billions upon billions of point charges slamming into the plane all at the exact same moment. So how in the world do we even begin to calculate the massive electric fields generated by a storm like that?
Now this leads to a brilliant paradigm shift. For a really long time, physicists used Coulomb's law to measure the strength of this push and pull between charges. And Coulomb's law is great. It's like tracking a conversation between two people. Super easy for simple setups. But what if you have a massive metal sheet, or a lightning bolt packed with billions of charges? Trying to use Coulomb's law for that is literally like trying to calculate the force for every individual grain of sand in a massive pile. It would take a lifetime of math. But then Carl Friedrich Gauss came along. Gauss realized, hey, we don't need to count every single grain of sand if we just know the weight of the whole bag.
Gauss totally shifted our focus from those individual tiny charges to the big picture. He invented something called a Gaussian surface. Now this is just an imaginary envelope that we draw to match the shape of whatever object we're looking at, like drawing an imaginary cylinder around a long wire. By doing this, we can just look at the total flux, which is the total number of those invisible field lines passing through our imaginary envelope. Gauss's law doesn't replace Coulomb's law, it just absolutely supercharges it. It makes the impossible math completely simple.
The formal rule basically boils down to this. Gauss's law states that the flux of an electric field through any closed surface is exactly proportional to the total charge enclosed within it. This means the math totally relies on what's inside the shape. If you draw a closed boundary and the total net electric flux flowing out of it is zero, you can conclude with absolute mathematical certainty that the total charge contained inside that closed surface is also exactly zero.
All right, so look at what we've gathered. We know opposite charges attract and like charges repel. We've got Faraday's invisible webs of electric fields. And we have Gauss's imaginary envelope that gives us the big picture shortcut. With all these concepts connected, let's head right back into the storm, to the climax of our mystery at 35,000 feet. When that massive, chaotic burst of lightning strikes your plane, you'd probably think, okay, millions of volts, it's definitely going to blast right into the cabin. But here is the secret. The airplane's metal skin is an incredibly good conductor. It acts as a literal superhighway for electricity. The very split second the lightning hits, those millions of volts of charge hit the gas and move across the metal at nearly the speed of light. And because of Benjamin Franklin's early clues, remember the law of repulsion? It's kicking in big time here. All that excess electrical charge from the lightning bolt is made of electrons, and electrons absolutely hate each other. They actively want to get as far apart from one another as mathematically possible. Now, since an airplane is essentially just a giant hollow metal tube, the absolute farthest these repelling electrons can physically get from each other is by rushing instantly to the very outer layer of that metal skin.
And this is where all our clues lock together to build a rock-solid proof for why you survive. If we treat the long, tubular body of the plane with cylindrical symmetry, we can map out exactly what's going down. Step 1. Lightning hits the metal skin. Step 2. All those electrons violently repel each other to the absolute outermost layer of the plane. Step 3. This is where Gauss's brilliance shines.
If we visualize the airplane as a hollow, spherical shell, kind of like a big blue ring loaded with negative charges on the outside, we can literally see the math in action. If we map out the area inside that hollow space where you and the other passengers are sitting, how much charge does it actually enclose? None. Zero. By Gauss's law, if the enclosed charge is zero, the electric field is zero. This principle mathematically proves exactly why the interior of the plane is a completely dead zone to all the electrical chaos outside.
So, to summarize our cinematic case study, your survival up there in the storm isn't a miracle. It's simply the brilliant reality of a hollow conductor shield. The plane acts as a giant hollow metal shell. The lightning's angry electrons intensely repel each other and spread exclusively over the outer skin of the aircraft. The interior space where you're calmly drinking your coffee remains a perfectly neutral zero-field zone, and the passengers stay entirely safe. This phenomenon is often known as a Faraday cage, and it is a pure, life-saving application of physics in action.
So, when you step back and look at the whole thing, what a journey, right? A single chain of discovery stretching across more than 2,000 years. From Thales and his chunk of amber, to Gilbert giving the force a name, to Franklin figuring out its dual personality, Coulomb measuring its strength, Farragut imagining its invisible field, and finally Gauss giving us the elegant shortcut to make sense of it all. And I guess that's really the heart of this whole story. The fundamental laws that run our universe, they're often breathtakingly simple. But the journey to actually find them, to peel back all the layers of what looks like impossible complexity and reveal the elegant truth hiding underneath, now that is the true adventure of science.